Okay, thank you very much. So similarly, as in the case of Leila, so I cannot thank myself. So maybe I thank Leila for sharing the organization with me. And really, I want to thank you all for your participation, active participation, I would say, for what appears to be a rather successful workshops so far. Okay, so my talk is related to a few talks, a few previous talks, specifically the one by Mochizuki and Tsujimura and Minamide also to some extent. And so I want to talk about the arithmeticity of the mapping class group. All right. So this is a joint ongoing project with Mochizuki and Tsujimura. All right. Okay, so first of all, I would like to fix some notations, and we have seen a few of these notations previously. So G and R are a pair of integers which satisfy the usual hyperbolic condition, right? So 2G minus 2 plus R is positive. So in my talk, without loss of generality, I will assume that R is positive. So I will be considering surface groups of affine curves and affine hyperbolic curves. So pi GR is the profinite surface group. So profinite completion of a surface group of type GR. So in this case, it is profinite free. And for a positive integer m, so xm will denote the mth configuration space of a hyperbolic curve x of type GR over an algebraically closed field K of characteristic 0, right? And pi mgr will denote the fundamental group of xm. So this is a classical object which appears, at least in the discrete case, in topology. So this is related to the braid groups, the Artin braid groups, and so on. And we have heard of combinatorial anabelian geometry in several talks in this workshop. So combinatorial anabelian geometry evolves around the study of automorphisms or outer automorphisms of these fundamental groups of configuration spaces. So this is one of the main topics of study in combinatorial anabelian geometry. And then so I want to state a result in combinatorial anabelian geometry. So we have these out groups or out F, which appeared in several talks. So let me recall briefly what are these. So the notation out stands always for outer automorphisms, so automorphisms modulo inner automorphisms. And these out F, out FC are subgroups of the group of outer automorphism. So what is out F? So we were reminded in the talk by Minamide that if one has an automorphism of pi mgr, then this such an automorphism preserves the fiber subgroups, so the subgroups which arise from projection onto configuration spaces of lower degree, but it preserves them globally. So it maps a fiber subgroup to possibly another fiber subgroup. So this out F consists of those outer automorphisms or classes of automorphisms which fix each individual fiber subgroup. So it just maps a fiber subgroup to itself. And inside this out F, there is out FC. So out FC is a subgroup a priori of out F. So this consists of all elements of out F with the following property. So you have various called adjacent subquotients of pi m gr, which arise as subquotients of projections between configuration spaces with consecutive degrees. And so these are surface groups. So this out FC consists of elements of out F with the property that they induce automorphisms of these profinite surface groups with the property that they preserve the conjugacy classes of inertia subgroups. So globally, they map conjugacy class of an inertia subgroup to another conjugacy class of an inertia subgroup. So this out FC a priori is just a subgroup of out F. So one of the main results in recent times in combinatorial and abelian geometry is that these two groups are equal. So this condition, this C condition, is automatically preserved. So this is quite important result. And the other result, which was, I guess, somehow known in the case of out F, is that this group stabilizes when M is large. So when M is large, for example, here, when M is at least 4, then all these groups are naturally isomorphic or even equal. So, and by definition, out F pi GR infinity is equal to out F pi GR M when M is at least 4. And in the case, in the 0,3 case, so this is related to GT. So this is what we have seen in various talks. So GT appears naturally in the study of these configuration spaces. Okay, so the upshot somehow of my talk is this commutative diagram of exact sequences, which appeared under various ways, especially in the various explanations and discussions by Mochizuki. So this is the main topic of, so my talk is surrounded around this commutative diagram. So I have to explain what the objects are here. So first of all, so the upper exact sequence, so this is, so MGR is the moduli stack of hyperbolic curves of type GR over Q, and pi MGRQ is the fundamental group of this in the sense of stacks. So this one has such an exact sequence. So out F pi infinity GR, I have just discussed this. And then one has a map. One has this middle vertical map from pi MGRQ to out F pi GR infinity. So the fundamental group of MGRQ acts on the fundamental group of configuration spaces by outer automorphisms. So this action arises from the various projection from MGR plus M to MGR, where you fix, where you order the M additional points. So pi MGR acts on the fibers of, or acts on pi one of the fibers of such projections, which are configuration spaces. And this map lands in out F. So it lands in out F. So that's the map. So, well, this map, the right vertical map is the map that appeared several times in this workshop, namely the map from GQ to GT, which is known to be injective, right? And what is somehow new in this picture is this map here, which is the tripod homomorphism. And this is the map that Mochizuki discussed last time and this morning, right? And the definition of this map is highly non-trivial. So one has various copies of the fundamental group of P1 minus 3 point over Q bar, which appear in this pi infinity GR, and such an element of out F of pi GR infinity, and uses automorphisms of these copies. And what one shows is that essentially what one gets is essentially the same automorphism. So this is a highly non-trivial result, and Mochizuki discussed this morning a little bit the history of this map. And this map has the property to make this square commutative, so one gets this commutative diagram. So this out F pi GR infinity geometric is by definition the kernel of this tripod homomorphism, right? And so one has this picture, and I want to emphasize again that this picture is somehow new, because this tripod homomorphism is new, or relatively new. So one gets this picture where, so the upper exact sequence, so this is of arithmetic and geometric nature, and the lower exact sequence, of course, is of combinatorial group theoretic nature. And the natural question is, how do these two exact sequences relate to each other? Yes? because this is what I said. So when m is bigger or equal to 4, so there are various natural maps from out f by m plus 1 to out fm, etc. And they are just isomorphic, so they are.
You mean canonically isomorphic?
Yeah. Okay, and so as I said, so we want to the natural question is to compare these two exact sequences. So already the issue of comparing GQ to GT appears several times, and one knows about this. So here, for example, the issue of the injectivity of the left vertical map is closely related to the congruence subgroup problem for the mapping class group. So it's essentially equivalent, and so as I said, it's natural to try to understand the gap somehow between these two exact sequences. Of course, if one is optimistic, then one can hope that these two exact sequences are just the same. They just collapse to each other, right? So GT is GQ, and this is this, and this is this, right? So this is this is the kernel of this. The kernel of this, yeah. So a priori, it's not clear that this is surjective. Yeah. Okay. So and the result or the project that I'm involved in and I want to discuss evolves around this picture here. So first of all, I want to define this out FGR. So this group is a GT group, so it projects onto GT. So we don't know that GT is GQ, of course. So we want to use the GQ version of this. So I will refer to this as the arithmetic version of out F by GR infinity, right? So just the base change or the pullback by GQ, right? And what we aim to prove, of course, when you do this pullback, you still get a map from pi mgrq to out fgr, and the aim is to prove that this map is surjective. Right, so maybe I explain, I write briefly what happens when you pull back this. So one has pi mgr. So one has this sequence, and then one has out f, this out f geometric. So this is the out f geometric there, and then one has this out f gr, and then gq. So this is already the pullback to gq, and one has this map, and then one has the out f by gr infinity and gt. And here one has out f go, right? So this is the picture. So we pull everything back to GQ, and the aim is to prove that this map is surjective. Right, so this is surjective. Of course, if it turns out that GT is GQ, this just implies that this map is surjective. But at any rate, what one obtains as a corollary of this is that this map is always surjective. Right? Okay, so and you can see, so for example, what I said, if it turns out so that this is these two are isomorphic or these two are isomorphic, so what one obtains is really a profinite and even arithmetic analog of the Baer-Nielsen and then theorem. Okay, so let me.
Basically, theorem A and theorem B are equivalent, right?
Yes, yes, yeah. But somehow to prove corollary B, we need this diagram. So if you forget about this, it's not clear how to prove that this map is surjective. Yeah? So we use the arithmetic somehow. Okay, so in fact, to be more precise, what we want to prove is the following. So these two groups, so both groups, these two groups act on the surface group by GR by outer automorphisms. So we can form the outer semi-direct product So this is the outer semidirect product of this by pi gr, and this is the outer semidirect product of out f gr by pi gr. And this is the map that we are considering, and we are trying to prove that it is surjective. And in fact, what we want to show is ultimately that this map is surjective. Of course, which would imply that this map here is surjective, right? So this is quite similar to what happens in Tsujimura's talk. So in fact, in Tsujimura's talk, if you remember, so what was being compared is not really GT and GQ, but GQ outer semidirect product of pi x and GT outer semidirect product of pi x, where x is the P1 minus 3 points. So we want to show that this vertical map is surjective. And again, so the observation is that on the left-hand side, you have an object which is of a scheme theoretic nature, and on the right-hand side, you have an object which is combinatorial. So to be more precise also, in fact, what one aims to prove is the following. So given any finite characteristic center-free quotient of the surface group pi gr. So by the way, as it was observed by or mentioned in the talk by Mochizuki, so these kind of quotients are cofinal. So and if you have such a quotient, because it's characteristic, so pi mgr and out fgr also act on such a quotient, and you can form via outer automorphisms, you can form the outer semidirect product, and you still get such maps, and we want to show that such a map is surjective. Now, if you think about it, what you want to do at first glance, so you want to construct a family of covers of hyperbolic curves of type GR, a family over a base which is, say, finite étale over the moduli space MGR, a family which is both on which this group acts. So we want to construct a family of covers of curves of hyperbolic curves of type GR over a base which is finite étale over MGR on which this group acts. But you want a family which is both connected and the base is also connected. So that's the main point. So there are 2 points here. So the construction of such a family, and then the issue of connectedness, which appeared several times in the talk by Tsujimura and Mochizuki, also the study of idempotence. But in fact, the proof does not go that far. But as I will explain in the proof, so we will come very close to constructing such a family. And that's the point. So I have no intention to go into the full details, and as it was mentioned by Mochizuki, also the details are, so one is still in the process of writing out the details, but I want to explain some of the main ideas in the proof. So first of all, I want to explain how to try and construct such a family of covers on which this group act. So first of all, what one does, one constructs the fibers of such a sought family, right? So first one constructs the fibers of this such family, and this construction uses an abelian geometry, right? So this is somehow the first step. So we want to construct covers of curves which will somehow play the role of fibers of such family that we are looking for, and these fibers will be labeled by this out f. So an abelian construction of out f gr labeled coverings and curves and so on. Okay, so how does this work? So you start with a closed point in mgr, right? And so this gives rise to quasi-section of the projection from pi mgr to GQ. So F is a number field. So this is GF is an open subgroup of GQ. And you have a section or quasi-section from GF. And of course, this section is only defined up to conjugation, right? And now if you look to this section and then you pull back the upper exact sequence in in this diagram, or even the lower one by this section. Of course, the section is here, but it gives rise to a section inside out FGR. So remember always this out FGR is the arithmetic version, so it always projects onto GQ. Right? So if you pull back this extension by this section, you get a group extension of GF by pi GR, which in fact is isomorphic to the arithmetic fundamental group of X, right? And then for any element of out FGR, you can conjugate the image of this section. So this section has an image also in out FGR, so you can conjugate this section by sigma, right? And we want to construct objects, curves, and covers, which are labeled by this sigma. So when you conjugate the image of this section by sigma, and again you pull back the exact sequence that I just mentioned by this section GF sigma, you get another group extension of GF sigma by pi GR, which as a group extension is just isomorphic to pi of X. But to this group extension, or starting from this group extension, you can reconstruct in a purely group theoretic way various arithmetic and geometric objects, right? So what we are trying to do here, we are trying to justify somehow the arithmeticity or the geometricity of this GF sigma, right? Yeah. So starting from this group extension, we construct a number field. F sigma is a number field. F sigma bar is its algebraic closure in such a way that GF sigma is the group of automorphism of this extension. And also we construct a hyperbolic curve, X sigma of type GR, and we reconstruct the ring of regular functions on X sigma. And more generally, so this construction is purely group theoretic, so just starting from the group extension pi X sigma. So more generally, if you have a finite characteristic center free quotient Q of pi GR, and you have an element sigma, if in out F, outer semi-direct product with Q, then to such an element corresponds an open subgroup of this pi X sigma. And again, from this open subgroup, or to this open subgroup, you associate various objects, or you construct various objects. So you construct a number field, Fy sigma, and an algebraic closure, Fy sigma bar, hyperbolic curve Y sigma, its ring of regular function, and covering, a finite étale covering, Y sigma X sigma, which is geometrically Galois. Geometrically Galois with Galois group Q. Now, yes.
What is the Fy? What is the so Q determines the geometric covering?
Yeah. But it's geometric. So this Fy sigma would be the field over the number field over which Y sigma is defined.
Yes. So okay, my question is so what is this open subgroup? Pi by sigma?
Yeah. So one associate to this sigma, this open subgroup. So one.
But so Q determines the geometric covering. I know. But so
Yeah.
How to
yeah. So this I did not explain in detail, but one associates such an open subgroup. Yeah. So it's So one looks to the kernel of the outer action of out FGR into Q. So this is, and so one has to do something, but essentially to such a sigma you associate such an open subgroup. Yeah. But this has to be done at this level. Okay. Okay, so this the construction, as I said, is group theoretic and abelian, but the emphasis here is on the function spaces approach. So what one does, in fact, is the following. So in reconstructing this F sigma, X sigma, and OX sigma, so for example here, what one does first, one constructs this field F sigma, right? So one constructs F sigma by using Kummer theory, right? And also using the inertia subgroup. So this is why one assumes that R is positive. So the Kummer exact sequence and restricting to inertia subgroup. So one recovers the multiplicative group somehow of the scalars, and then one defines additivity just by transport of structure, right? And then one constructs an algebraic closure of F sigma by passing to open subgroups inside pi x sigma, and then one constructs these F sigma bar closed points of this sought curve somehow x sigma. So these closed points are constructed as conjugacy classes of subgroups in this extension pi x sigma, right? So the conjugacy classes of subgroups, in fact, which arise from the decomposition groups inside pi of x via any isomorphisms. It's independent of such an isomorphism. And then once one constructs such a function space, one constructs this OX sigma just by transport of structure. So this function space is isomorphic to the function space associated to the original x, and then inside which one has OX, and then one just takes the image of this OX, which we call OX sigma. So this approach is not quite usual in abelian geometry, but it plays an important role in the proof of this. Yes.
So are we constructing like fiber above X, right? The goal at some point was to construct covers of NGR.
Yeah, yeah. So for each such a sigma, we are constructing such an X sigma and such a Y sigma.
Sigma is just in Q, not in the secondary part. It's just in the left-hand side.
Here it is in the semi-direct product.
Sigma is in the whole thing.
Yeah. Sigma is the whole thing when you consider covers. But one special case here, when Q is identity, you just reconstruct X sigma. You constructed the original curve. But then we let Q vary, and then we construct the various covers, the various Y sigmas. So when Q vary, of course, you are looking to family of covers. Yeah. But coming back to your question, so ultimately, as I will explain, so only finite quotient of this will play a role, and then we will have only finitely many fibers. But maybe what I said at the beginning is somehow misleading. So we will, I said precisely, we will come closer to constructing such a family. We will not construct, in fact, such a family precisely.
And outer semi-direct product just means non-split extension?
This is the, no, this is.
Outer automorphism group acts.
Yeah, on Q, and this is center free.
Properly outer.
Yeah. It acts like a true edge.
Yeah. It's an outer automorphism group of something else.
Yeah.
Kind of. But is it just a semi-direct product?
No.
No section. In general, it doesn't have any section.
Okay, so it's like a non-split extension.
Yes.
Yeah.
Yeah. So this is the exact sequence. So we saw because Q is center free, so one has this exact sequence, and these are just the pullback, right?
So the semi-direct symbol really just means it acts as outer automorphism.
Exactly. Yeah. Okay. Yeah, just the definition. So the definition of this outer semi-direct product is this. Yeah. Okay.
It's only possible when Q is
center free. Yeah. So because you have such an exact sequence when Q is center free. Okay. Okay. So now if you have two elements, sigma and tau, in this outer semi-direct product, so this is somehow the picture that appeared in the discussion by between Mochizuki and Mignon Kim this morning. So if you have two elements now, sigma and tau, in outer FGR, outer semi-direct product of Q, then you have these two objects or two coverings, one labeled sigma and one labeled tau, and these are related by inner conjugation inside this group, say by such an element. So this should be Q outer semi-direct product, and this relation is combinatorial. So a priori it's not geometric, and this corresponds to the dilation that appeared in the talk by Mochizuki. So this is similar to the dilation which he mentioned and which appeared in appears in classical complex Teichmüller theory. So this dilation is a priori combinatorial, not geometric. And what we want to prove, in fact, is that this element is an element of pi mgr. So this dilation is geometric, right? So what you want to do, you want to compare the object labeled sigma with the object labeled tau. So what you want to do, so one naive approach is that, of course, you have these function spaces labeled sigma, labeled tau. You have the functions labeled sigma, labeled tau, which are contained in here, and you have such a natural diagram where the horizontal maps are natural identifications. But this turns out to be meaningless. So if you want to try to do this, you won't achieve much. So it's like you are trying to. So in the talk of Mochizuki, remember, so you had the sheaf of complex analytic functions corresponding to two different complex structures on the same surface. And what one does, one embed them into, if you want to compare them, you embed them into the sheaf of real analytic functions, right? And one wants to do something similar here. So what will be meaningful is the following. One wants to construct a non-labeled function space. Non-labeled function space which somehow lives at the level of out FGR. So one wants to construct a copy of Q bar, which is non-labeled and which is an out F copy somehow. And one wants to construct closed points of curves or coverings of curves which are non-labeled and which live at the level of out F. And what one wants to do achieve such a construction such that the various labeled objects that we constructed embed naturally in here. And so in this single function space, now you try to compare these two labeled objects. So this function space will play the role really of the sheaf of real analytic functions in the example which was discussed by Mochizuki. And you want to compare them using group action. So the group action that you had is the action of this group. So you want this group to act on these function spaces. Yeah, so in a way which is compatible with these labeled objects. So that's the task somehow, right? So I want to explain briefly how this is done. So first, we want to construct a single copy of Q bar, an out F copy, or it was referred to in the talk by Tsujimura as a combinatorial copy. So this Q bar combinatorial would be an out F version of Q bar. So how one does this? So one does this using the map from GQ to GT, right? And so GT acts on pi 0.3. And so if you pull back, again, pi 0.3 is center free. So if you pull back the composite of these sequences by the sequence which is analog to there, where you take Q to be pi 0.3, so you get a group extension. You get a group extension of GQ pi 0.3, which is isomorphic to the arithmetic fundamental group of P1 minus 3 points. And then essentially using the same technique that I explained for X sigma and Y sigma, you can reconstruct a copy of Q bar, which is Q bar combinatorial copy, so Q bar comb, but I will use the notation M. So this M would be a copy of Q bar, which is constructed in this way. And of course, the various F sigma bar that we have constructed are in natural, you can identify them in a natural way with M. So and we will do this from now on. Also, you can reconstruct the closed points of the tripod over with values in M, so P1 minus 3 points. You can reconstruct the cusps and so on. So we want to use the points of P1, right? So we want to use P1 in somehow essential way for various reasons. So first of all, we want a labeling. We want a labeling on points. So I will explain how this labeling appears. So first of all, of course, we can choose a labeling of points of P1, and we want to use this labeling to label the closed point that we want to construct, this act point that I mentioned. So anyway, we want to relate curves to P1. And of course, this can be done by coverings. So we can take just coverings to P1, but there are various coverings. So the most simple coverings are the simple coverings, right? In the terminology, the well-known terminology. So if you go back to the construction that I discussed, so for such an X, right, we fix a D, which is bigger or equal to G plus 1. So for such a D, you can always find a simple degree D covering of the compactification of X above P1. So simple means that in the fiber of every point, so all points are ramified apart from one with ramification index 2. And then you choose a section of this projection, right? So M valued points here project onto P1, and you choose a section, and via this section you get or if you look to the image of such a section, you get an infinite set of points of X closed points which are labeled. So they have a labeling, they inherit the labeling that we have fixed, right? And then also you get a labeling of the fibers of these points in the cover Y. Also, there is a sigma version of this. Namely, if sigma is in out F, then so this, right? So you get, sorry, actually maybe I should assume that sigma is in out F, outer semi-direct product of Q. So you get sigma version of X, a sigma version of Y, and this simple covering F gives rise to simple covering F sigma, and also this section delta F gives rise to section delta F sigma. And then if you use this in the same way as I explained, you get also points which are labeled via the tripod labeling. So we refer to this as the tripod labeling, but here which are also labeled by out F or out F semi-direct product Q. But you will see, so we will get rid of this labeling. So somehow only. Yes. Yeah. Sorry. Y sigma is the covering. Yeah. Yes. P1. No, just P1. Sorry, P1. Non-labeled. Yeah.
What do you mean by
bracket. So yeah, this is just the fiber of X alpha I in Y. Fiber set, elements of fiber. Yeah. But we don't want to label the elements in the fiber as well. So it's not necessary, in fact. Okay, so in fact we will work with Hilbertian points. So we want a version of these points which satisfies certain property, right? So ultimately we will work with infinite set of points within these points which satisfy certain Hilbertian properties. So the Hilbertian property plays a crucial role here. And so we have the notion of a Hurwitz datum. So Hurwitz datum is just a point X, simple covering F, and this section delta F. And ultimately, we will let this Hurwitz data vary. So we will work over the moduli. Okay, so we want to construct points, out F active points. So this is somehow similar to the GT point that were discussed by Mochizuki this morning. So the idea is so our points live in these hyperbolic curves of type GR. So we want to think of these points as cusps. So we start removing them, right? And if you start removing them, so instead of pi GR, you will be working with pi GR plus 1, plus M, where you delete M points, and ultimately you work with pi GR plus infinity, right? And so the tripod labeling that I discussed will be related to the labeling here M or infinity, right? So anyway, so we want to construct these active points as inertia subgroups or conjugacy classes of inertia subgroups. So we want to pass from pi gr to pi gr plus m or and so on. So remember, we are working with out f pi gr or out f pi gr, outer semidirect product of with q or pi gr. So we want to ultimately to pass to out f pi gr plus m. But a priori, there is no map from this to this, right? So one has to consider a subgroup, this subgroup out f pi gr plus absolute value m. So what is this? So these are the outer automorphisms here, which preserve each fiber subgroup, so they are in the F, but with the property that they preserve each conjugacy class of cuspidal inertia subgroups in here, which corresponds to the label from R plus 1 to R plus m. Okay, and then this maps to out f pi gr. So one has in fact such an exact sequence. So this is also more or less, I think, a new result in combinatorial Abelian geometry by Mochizuki and Tsujimura, but which appeared already more or less in paper by Mochizuki, Tsujimura, and Hoshi. Not in this full form, but anyway, and we want to consider also the arithmetic version of this. So we base change to GQ. Now this group acts on the surface group pi gr plus m in a natural way, and then we take the limit when m tends to infinity, so we get this. Now the kind of points that I consider this x alpha, which are in these sections, which are labeled by the tripod labeling. In fact, they correspond to inertia subgroups here. So they correspond. So it's just the projective limit of this when m goes to infinity. Yeah. Okay. So these points correspond to cuspidal inertia subgroups here, right? And we define the active version of such a point x alpha as the conjugacy class of such corresponding cuspidal inertia subgroup, conjugacy class by this full pi gr plus infinity. And likewise, if y alpha is a point in the fiber of x alpha in this corresponding over ym over xm, then we define the active version of this point as the conjugacy or the active version of the fiber of this point as a finite set of conjugacy classes of this cuspidal inertia subgroup by left cosets of this subgroup. So this subgroup is the kernel of the projection of pi gr plus infinity to q. Okay, so we get this active version of the points, and also there is a sigma version of this active point, but the sigma version just arises by conjugation. Namely, if you have a sigma here or a sigma here, then you choose some lifting in here and you act by conjugation on these cuspidal inertia subgroups. Then so such an action preserves the cuspidal inertia subgroups. It maps it to another cuspidal inertia subgroup because of this definition, this absolute value, and then you get a sigma version of the active points of x and y. And the construction is done in such a way that you get such identification. So the function spaces labeled sigma are naturally identified with this single function space. And in particular, here you have the ring of functions labeled sigma. You can map it here, and we look to the images. So in some sense, this has achieved the goal of constructing this single function space. So this is the single function space plays the role of a common container to these various OY sigma and OX sigma. It's inside this that we want to compare this. And of course, remember, we want the action. We want an action of out F or out F semidirect product with Q on this single function space. That's quite important because we want to use this group action to compare these labeled objects. And again, here, so the point, so one can show there exists a finitely generated subgroup of this, right? And a finite subquotient of R, so this NQQ, which has this form here. with the following properties. So first of all, the outer action of NQ on Q captures the outer action of out F on Q. So this is important because we are interested in the monodromy of out F on Q. We don't want to lose it. And the other property is that, so of course, R or this acts on the various labeled copies of this ring of functions. And the point is that such a finitely generated subgroup acts on the ring of on the various OX sigma as identity. So we have a single copy of the various OX sigma bars. So this I will refer to OX mod. And for the OY sigma bars, or the OY sigma, it acts via this finite quotient NQ. So we have only finitely many labeled copies in OY sigma bar. Okay, so in my talk, I will be not very precise in the following sense. So later, so this group will appear, but actually this should be replaced by R, or the image of R in out F, outer semidirect product of Q. But this is not quite important. So just a remark about the active points. So why they are called active points. So these points will be subject to deletion. Right, so as Mochizuki said, so these are active points. So they are like soldiers. So you are sending them to war, so they might die. But we need some fixed points because we want to use a moduli space, right? And we want to use a moduli space of pointed curves and pointed covers and so on. So we want a fixed point x0 and a fixed point in the fiber of this x0, which are not which are fixed, which are not object to deletion. So I will just skip this. I will just skip this. And the idea, so you pass from GR to GR plus absolute value of 1, and then you get such a point, and also you get splitting of this sequence. So I don't want to, I have to skip this, otherwise I won't be in time. So anyway, at the level of active points, we have these active points, so the fixed x0 and these points, and at the level of y, we have the fiber of x0, and we have a single point here, which is fixed, and then we have all these fibers. Okay, now, as I said, we want to work over the moduli, right? So this is the moduli stack. So this is the universal curve over M. So all squares here are Cartesian. So we just base change this to M1, which is GR plus absolute value 1. So the absolute value here means that the added points are ordered. And then we consider a cover, finite étale cover of X mod 1. Which is, again, constructed in an ad hoc way. So this corresponds to the following open subgroup of pi x mod, right, which is constructed via a tautological section of this, right? So maybe, again, I will just skip this. So anyway, this is a finite étale covering, right? And we base change it to M infinity, and finite étale covering of X mod, which has, so this has a moduli interpretation, right? So, and we want to use this moduli interpretation. So we want to use it in the following way. So first of all, we shrink X mod infinity, so we can assume that it is affine. So we're just working with a ring of functions. So we let the Hurwitz datum vary. So we consider this huge product of function spaces, which are labeled by the various Hurwitz data. And then by the moduli interpretation here, we can map this ring of functions inside this infinite product of function spaces. So each OX mod infinity maps to each of these OX mod. And likewise, for an element in NQQ in this finite subquotient that I mentioned, so we have an embedding of OY mod infinity inside this infinite product of function spaces. And right, so I will denote image of OX mod infinity. This infinite product has OX et al mod infinity, and then one has a version of OY et al mod infinity, a version of this family of covers labeled by alpha for each alpha in this finite sub quotient. And then what one does is this construction that appeared in Tsujimura's talk or in Mochizuki's talk. One takes the sub algebra, the sub Rx mod algebra inside this infinite product of function spaces, which is generated by these finitely many copies of OY mod infinity, right? So this, as was mentioned, yes. X mod, this one?
Yeah, the X mod and the Y mod.
Yeah, so the X mod is the universal family of curves, and the Y mod is, yeah. So the So first one, so this is the universal curve. We base change it to this in order to construct this finite eta cover, and then we go to infinity. We just base change. Okay. So this is again, after so this is an Rx mod algebra. So after possibly shrinking the base M, we can suppose that it is flat. So then it is finite et al. And this is how close we are. We come to constructing this family of covers that I mentioned at the beginning, right? So the issue here is about the connectedness of this RY mode, whether it is connected or not, right? And so this is the analysis of idempotent. So this is how close we come to constructing this family of curves. So this, if this would have been connected, then one is done somehow. But we don't know, of course, we don't want to study the idempotence of this algebra. And here comes this combinatorial algebraization theory that Mochizuki mentioned, and this lemma, etc., which allows you to study idempotence of such algebra inside such a function space. Yeah. Yes. No, just so we shrink the moduli to work with affine objects. Yeah. Yes. Yeah. Okay. So in order to analyze the idempotence, we project into a single Hurwitz datum. So and we want to use this result that was mentioned by Mochizuki and appeared also in the talk by Tsujimura. But if you remember, this result is relative to a fixed curve over a field. So here we have a family of covers. So we basically we project onto a single function space which corresponds to a fixed Hurwitz datum, and inside this function space we have the ring of functions of OX, and we have also these finitely many copies of OY alpha. So I will switch from the notation sigma bar to alpha, and so we take the sub algebra generated by these, and then we get this map here. And we map the idempotence here to the idempotence here, and we study the idempotence of Ry. And right, so we take a maximal set of idempotence of Ry mod, and Q acts on this idempotence, and we map them now to Ry. So these are this is the non-zero image of the idempotence of this idempotence of Ry mod inside this Ry, and then this is the result that was mentioned by Mochizuki, right? So namely here, so what happens is that there exists an infinite subset of this set of active points, the dagger subset, with the following property. If you look to the fiber of this subset within the set of active points of Y, then you have this function space, which is projection of the original function space, and then you can map the various objects that you had, Ry, Rx, etc. So the dagger version are just the images of this, and so this is the image of the idempotence. So of course some idempotence might go to zero when you restrict in this way, but the point is that the non-zero idempotent, or the non-zero image of this idempotence, they form a Q orbit. So the action of Q on this is transitive. So this is the result that was mentioned by Mochizuki in his talk. And this is the main starting result of the theory in some sense. Because what this tells you, it tells you that something strange is happening here. So what acts on the idempotence a priori is out F, outer semi-direct product of Q. But out F here has disappeared, right? So, so this is somehow the main result. And as a corollary of this result, one obtains the following. So this was also mentioned briefly in Tsujimura's talk. So again, we are using a single Hurwitz datum, so X defined over some number field, and then if you descend your curve, say K naught is a number field over which X is defined, so it comes from some X naught, which is over K naught, and then K over K naught is some infinite extension, such that Y, your covering is defined, Y to X is defined over K, but in such a way that Y over X0 is Galois also. So you have such an exact sequence. Then as a corollary of this Q transitivity property, you get a map. You get a map from NQ to this Galois group, to the Galois group. So you get a map between, so this is the out F. So this is somehow the arithmetic portion of out F. So this is a quotient of out F. And so this acts on the arithmetic portion of your cover, right? So, so this is not very so, but this uses this Q transitivity property. Yeah? So again, unfortunately, I'm sorry, I cannot go into the details, but the point is that, of course, this acts on Q, right? So via this map, you get a new action of NQ on Q, which is somehow mysterious. Of course, if everything is okay, namely if pi mgr, say, is equal to out F, this would be just the natural action of NQ on Q, right? But here, a priori, we do not know what this new action is. So anyway, so this transitivity result also applies here over the moduli. Namely, remember, this Ry mod is inside this infinite product of function spaces indexed by various Hurwitz datum. And then what happens is that if for each fixed Hurwitz datum, you restrict the set of active points, and then you restrict the set of Hurwitz datum to a subset of Mg, which is Zariski dense. So what happens, you get the same result, namely the action of Q on the non-zero images of the idempotence of this is transitive also.
Is NQ finite?
Yeah.
I think the NQ
Yeah, but yes. Yeah.
Before,
Yeah.
you go to NQ, the map from NQ to low XQ, but the but the X over X naught is infinite.
Yeah, but here, as I said, I'm cheating a little bit. So I'm carrying NQQ, but this should be R or some. Yeah. Sorry. Yeah. So this is what I said. Yeah. So unfortunately, I was so busy I could not change my slides, but this NQ should be yeah. But in any way, so one obtains this Q transitivity, and in the same way, one obtains a similar statement to this statement here. One obtains a new mysterious actions of NQ on Q. So again, unfortunately, so this is and again, so this NQ should be replaced by some finitely generated groups, but at any rate, so what one has is the following situation. So one has this NQQ, and inside NQ, one has the algebraic part, which is the image of pi mgr q. And what we want to show that these two are the same, right? Because we want to show that the pi mgrq maps surjectively onto out F. So what happens is that one gets a map rho q from NQ to NQ algebraic, which is similar to the corollary that I stated previously. And as a result, of course, this acts on Q, and so via this mysterious map somehow, one gets a new action of NQ on Q. So this mysterious map is defined as a consequence of this Q transitivity on the idempotence. Okay, and so the last point, so what we want to show, in fact, we want to show that this map is just a section of this inclusion. So we want to show two things. So this map is just a section of this inclusion. And second, we want to show that this map is injective. Okay. And right, so I just say this few words and then I stop. So so first how to show that this is a section. So this again was briefly mentioned in the talk by Tsujimura. So one knows that the restriction of this row Q to the decomposition groups inside NQ algebraic is identity. And this comes from basically by construction from the case of a base which is a field or a single Hurwitz datum. But then this is generated by decomposition groups thanks to the Hilbertian property, right? So we use the Hilbertian property here. So in order to use the Hilbertian property, one has, of course, the moduli space is not unirational, so one has to base change to the Hurwitz scheme of simple coverings and use Hurwitz schemes of simple coverings. Ultimately, we want this D to be large in such that the map between pi1 of these Hurwitz spaces to pi1 of MG is surjective, and you use the Hilbertian property. And then to show that this rho Q is injective, what one shows in essence is that this new mysterious action of NQ on Q, which arises from this map, is just the natural action of NQ on Q. So this was explained very briefly in Tsujimura's talk. So the idea is to pass from GR to GR plus 1. So one works with a single fixed Hurwitz datum curve of type GR, and then considers the family of curves of type GR plus 1 over this, which arise from taking punctures inside this such a curve, and then one works with with the configuration space of type 2, the 2 configuration space over this and so on. So and one uses an argument which was very briefly mentioned by Tsujimura, this diagonal argument. Right? And here again, one uses the Hilbertian property. So one needs 2 types of Hilbertian points in this step, namely points which split completely and points whose decomposition group is as large as possible. So this is satisfied, guaranteed by the Hilbertian property of number fields over infinite extensions of number fields. One technical point here, which is quite subtle, is that in this process of proof, there is always this process of deleting points, right? And so in deleting such a point here, so in this step, one has to make sure that one is keeping infinitely many points of each type. And this is quite technical, but anyway, that's roughly the picture. So sorry, I'm over time, but okay, maybe I stop.